In this video, we are going to cover the extended Cox regression model, which is one of the models used to analyze survival time data when you have more than one independent variables. But what is this extended Cox regression model? Remember, in the standard Cox regression model, it assumes that the effect of each covariate or independent variable is constant over time. However, sometimes this proportional hazards assumption is violated. So, when that happens, we can use an extended Cox model where an independent variable's effect is allowed to vary over time. If this is your first video you're watching about Cox regression, we highly recommend that you check our previous episodes about the standard Cox regression so that you are able to better appreciate the concepts we are covering here. So the steps for fitting an extended Cox regression model are the same as the steps for fitting the standard Cox proportional hazards model, where we start by testing the assumption, choosing variable all the way up to interpreting and reporting the regression results. The main difference lies in whether the main assumption of the standard Cox model have been violated or fulfilled. If that assumption, the assumption of proportional hazards or constant hazard ratio over time, has been fulfilled, we use the standard Cox. But if it has been violated by any independent variable, then we go for the extended Cox regression model, meaning we have to start by checking for the assumptions of the standard Cox PH model. We have a previous video that goes into the details of checking for this assumption using the different approaches available. So in this episode, I'm just going to demonstrate using one graphical approach and then the global test to show the variable that is violating our assumption so that we proceed to fit our extended Cox regression model. Here is our hypothetical survival time data that we are going to use to demonstrate extended Cox in Stata. We have study ID, we have time to event, and then we have our event happening or not, that is death. 1 is for a death happening and 0 is for censorship. Then we have our 3 independent variables that we want to use to predict survival time of our participants. So we have to first assess whether our data fulfills the proportional hazards assumption, which is the main assumption for using the standard Cox regression. If it fails, that's when we can opt for the extended Cox. So for survival analysis in Stata, we have to first declare that our data is survival time data. Through statistics, go to survival analysis, setup and utilities, then declare data to be survival time data. My data is already declared. You can see we have the time variable. That's where you put your variable that shows the time to event. Then we have our failure variable. That is your variable having your outcome of interest with failure values defined here in our data set. A 1 shows that the event happened. Then we click OK. And in this output, we shall have the survival time data settings here. After this declaration, we are going to fit our standard Cox regression model and we check assumptions based on it. So we shall go to statistics, survival analysis, then regression models, Cox proportional hazards model. In this dialog box, we specify our independent variables. We have age, gender, and treatment. We can tell Stata that gender and treatment are categorical by putting I dot before the variable name, and then we click OK. So based on this standard Cox regression model, we are going to test for the assumption of proportional hazards. So we shall start by the global test or testing residuals. Simply go to statistics, survival analysis, then go to regression models, and then you see here test proportional hazards assumption. In this dialog box, make sure proportional hazards assumption test on based on scoring field residues is highlighted. Under options, you're going to tick this box of test proportionality assumption separately for each covariate and then accept, then click OK. Here are the outputs of our global test, which you would still get even if you had not specified that these are categorical variables. If I removed this and ran our global test, we could still get the same results like we had before when we had not shown that these are categorical variables, because the independent variables, the categorical independent variables we have here are binary. So whether we indicate or not, the results are the same. So we have for each independent variable, we have a row here, which is basically testing the null hypothesis that there is no correlation between the scoring field residues and time. If truly the hazard ratio, which is the assumption of Cox regression, are constant, then there should be no correlation between the scoring field residues obtained from this model and time. So when we look at age, the p-value here is non-significant, so it means the assumption has been fulfilled. Then we look at gender, the assumption has been violated. Then we look at treatment, assumption fulfilled. So overall, our model has violated the assumption of the standard Cox regression model. So we shall have to go for extended Cox so that we include this variable called gender as a time-varying covariate. We could also test the assumption graphically through statistics, go to survivor analysis, models, regression models. We can use the observed versus predicted, the Kaplan-Meier versus predicted survival. This tests one variable at a time and only categorical variables. So we can start with the treatment, then click submit. Here are our graphs where we have treatment A and treatment B, and for each treatment we have the observed survival times and then the predicted survival curve. If truly the assumption is fulfilled, then the predicted and observed for each category should be close to each other, like we are seeing right here. If we try the one for gender, which we saw previously as if it was violated, then we can clearly see that when we look at, for example, for female, the observed blue and green, blue is here up and green is really a bit far close from each other. Then towards the middle here, they come close, and then so this assumption, even graphically, it is violated. Same thing for the males. You can see that the observed and predicted are very far from each other. So meaning the variable gender violates the proportional hazard assumption. So we are going to use the extended Cox model, which accommodates variables such as gender, whose effect varies over time. To fit an extended Cox regression model, simply go to statistics, survival analysis, regression models, and again, Cox proportional hazards model. This is the same way we fit the Cox regression model, but under time varying covariate, we are going to check this box and include that variable that has violated the proportional hazards assumption, which is gender. And then under reporting here, we have got, by default, we shall get hazard ratios, but you may decide not to ask for hazard ratios, but report coefficients. So we are going to first submit, and we see our model. So in this output, we have the first part of the table for the main variables. Then we have the lower part for the time varying covariate, gender, which we have specified. And we can even see that it is statistically significant, meaning this variable gender, its effect varies over time. We could as well ask for coefficients instead of hazard ratios for our model, and we click OK, you can now see that our model is reporting coefficients instead of hazard ratios. But what I want you to appreciate is that the p-values obtained, whether you are reporting coefficients or p-values, they are the same even when you are reporting hazard ratios. When it comes to the interpretation of the extended Cox regression model, it is interpreted in the same way like the standard Cox regression model, except for the variable whose effect is varying over time, the time covariate in the lower box here. So we shall start by interpreting the model, reporting hazard ratios, and for that variable that has time dependence, we can see that gender has time dependence. So this hazard ratio, when we are interpreting it, since it varies with time, we have to interpret it relative to a fixed time point. So that hazard ratio is the natural log of the hazard ratio that compares males to females at time 0. We have to fix at what time are we interpreting this, when all other variables in the model are held constant and when there is no interaction between this variable gender and other variables in the model. If we are interpreting for the model having coefficients, then this value here, still for gender, which has a time varying covariate, then that value is interpreted as the difference in the natural log of hazard for males compared to females at baseline or at time 0. Still we are fixing time when all the other variables are held constant and there is no interaction. Like we saw in the interpretation of the standard Cox, when we are reporting hazard ratio, we are just talking about the natural log of the hazard ratio. But for the betas or the coefficients, we are talking of a difference in the natural log of hazard. I highly recommend that you go and watch the video of the interpretation of the standard Cox regression, because we cover all these concepts in detail. So next we look at how do we interpret the coefficient for the time varying covariate. For a model reporting coefficients, then this coefficient corresponding to the time varying covariate for gender here and of a categorical variable can be interpreted as the change in the natural log of the hazard for men that will occur for every unit change in time when all the other variables in the model are held constant and there is no interaction between gender and other variables in the model. Coefficients for other variables, age and the treatment, since they do not have a time varying covariate, they will be interpreted in the same way as the interpretation in the standard Cox regression model. So be sure to check out that video. If you found this video useful, consider liking and subscribing to the channel so that you don't miss out any of our episodes. See you in the next video.